We're going to do another example. This one is actually going to involve a two-tailed hypothesis test, and there's actually another catch to it as well, which we'll look at in a minute. So, records from a well-known Quidditch team shows that 6 out of every 10 passes are misplaced. Following the appointment of a new manager, it was found that in a sample of 20 passes, only 8 were misplaced. The previous manager stated that there was no difference in the way that they played. Investigate this claim to the 5% significance by finding the critical region, and I'm also going to find the actual level of significance as well, just because I can. The most important information here is 6 out of 10, and that is the general stats from the records, so that's actually going to be our probability. A sample of 20 passes, so that's going to be our sample size, and 8 is the result that we get in one of the trials, and that's what we're going to do the hypothesis test on. So we're looking at a 5% significance. Now, what is different about this one compared to what we've looked at before, compared to a one-tailed test, is that this person, the manager isn't saying they're better or they're worse. The manager is saying that there is no difference. And that's actually going to completely change the way that we actually address this problem. Because in previous questions where I've been able to say this can be modeled by the binomial distribution, again, we can check all the 4 criteria with sample size 20 and probability 6 out of 10, which is just going to be 0.6. What we would say in a one-tailed test is we'd say that the null hypothesis is p equals 0.6 and the alternate hypothesis is p less than or more than 0.6. But because here neither of those is actually stated, what I have to say is that p is not equal to 0.6, and this is going to change how we actually approach the problem. Because first of all, my 5% significance means that this is being split into both p less than 0.6 and p greater than 0.6, and my 5% significance is actually going to be split into those two, so that we're testing this to 2.5% and this to 2.5% as well. Unless stated otherwise, just divide the significance by 2. Occasionally, they will say find the value closest to 2.5%, in which case I can take values above or below it. But in here, because nothing else has been said, I'm just going to say I want to look at anything less than 2.5% and anything more than 2.5% from the end, which is going to be the same as 97.5 when we actually take it from the end. But this is the difference. We're actually testing both, and we have to divide the level of significance that they give us. There is, however, another problem in this question, because what I would want to do is I would want to look for the probability of my x value less than, let's call that R1, where I want to see when that happens to be less than 2.5%. So my 0.025, and I would also want to check p of less x greater than some other r value, which needs to also be less than 0.025. So if I have all of my probabilities here, I'm essentially capping it off at the bottom and at the top, so that this is 2.5% and this is 2.5%. So what this is actually going to correspond to is 1 minus p of x greater than or equal to R2, therefore has to be larger than 0.975, and we're going to look for the first value that hits that. So this is my 0.025 and this is my 0.975. And the problem lies in that what I would usually do at this stage, and when I'm looking to solve these, is I would look at my probability table. However, the probability tables do not exist for any probability greater than 0.5. And that's because you can always reverse engineer them. Now, with a calculator, you are perfectly allowed to create a list of cumulative binomial distributions with sample size 20 and probability 0.6. And if you are good at that, have a look at the previous video I did on one-tailed hypothesis tests. I actually talk you through that. Feel free to do that. That is probably easier. However, what I'm going to also show you is how you can still use the tables. The beauty of the binomial distribution is that binomial coefficients are symmetric. I know that 6 out of every 10 passes are misplaced, but technically if I look at it the other way, I can see that 4 out of 10 passes are successful. And I have probabilities for 0.4. So I can reverse engineer this to actually say, what if it's actually the other way around? It's exactly the same problem, but what I'm going to do instead, and I'll replace things in blue, is I'm going to look at it from the other point of view. So 4 out of 10 are successful, and we're still going to do a sample of 20 passes. If 8 are misplaced, that means that 12 are successful. So the previous manager states that there is no difference. So this actually just changes the point of view of the problem. The problem stays exactly the same. So we're still going to split the 5% significance, and we're still going to test to see whether this is realistic or not. In this case, though, I can actually use the tables. I'm still going to be looking for when does it go under 0.025 and over 0.975, because that has to do with 2.5% on either side, which I've nicely split here. So if I look at the tables, this time I can actually use them. What I get is this. It's all there, and essentially I'm looking for the points where it goes under 0.025, and that happens right here. So between 3 and 4, I have something that is less than 0.025, and then something that is greater than 0.025. So I've got x less than or equal to 3, and then here it goes over 0.975, so 2.5% from the end, when I reach x less than or equal to 12. I'm going to write this down. P of x less than or equal to 3 is the first value that is less than 0.025, and then P of x less than or equal to 12 is the first value that is greater than 0.975. So I need to again engineer this. I want to figure out from what value can I go up, and it's going to be 13 logically if 12 less is inclusive. So 1 minus P of x less than 12 is going to be less than 0.025, which is 1 minus that, which means that P of x greater than or equal to everything above, but because I've included 12 in the less than, it's going to have to start from 13, because these are whole numbers. So this number here will usually go up by 1 when you're dealing with it the other way around. So my critical region is anything under 3, but also anything over 13, including 13. So if anything is inside of these, that means there is enough evidence to 5% significance, or to 2.5 each side, that there might be something going on. And so once I have done this, then I can then use my kind of transformed data, whereas before I had 8 unsuccessful, I now have 12 successful, and I plant it into here. So my critical region will look a little bit different if I had done it the other way around. Logically, if it's 3 successes and 13 successes, if you did it the other way around, you will have found greater than 17 misses and then less than 7 misses, in which case the 8 would still fit in very well. So now that I've done this, I essentially need to do my hypothesis test. We have to set out, again for marks, just write this down, p equals 0.4 in this case, because we're doing it the other way around. H1 is p is not equal to 0.4, and that's the important bit here, which means my 12 is not an element of my critical region. It is just under 13, which means it is actually fine. So there's actually no evidence to reject H0. There is insufficient evidence to reject H0, which means we have to then put it in context. So the manager's comment is founded, and then if you really want to, you can say there is statistically, if you really want to say it, no difference in the way that they play. And then if they ask for the actual level of significance, I know that the significance level for 3, probability of that, is going to be 0.0160, and then the probability of x being greater than 13 is going to be 1 minus 0.9790, which is equal to 0.9790 0.0210. So the actual level of significance, instead of the 5%, because these are both less than 2.5%, is just going to be 0.0160 plus 0.0210, giving us 0.0390. So the actual level of significance is 3.9% instead of 5, because there's nothing between that and the when it goes over. There we go. You will rarely have to switch it over like that, but again, your calculators can do it just with brute force without having to use the tables, and you could have avoided changing all of this over if you're comfortable with using the list notation or just very good trial and error with your calculator. I'll leave that with you, and have fun.